All right, so we recap what we were trying to do. We're looking at branching process.
The recording is started.
Yes. Where we start with one individual, the number of children has is distributed as a random variable, the distribution of the organics. And each of these children reproduce their own children independently. We keep reducing. Now I just our notation number, we cover the probability that the process die down or probability of X litigation. And we have already characterized it in the terms of the probability generating function of X. That would be a done. So we also said another thing. Today we go to simply writing down the distribution of what we want to do today is the following. So if we call the definition of T, it is the total distribution T in the form T is equal to that for the same ID distribution. And what we want to show is that it's nothing but 1 by n x1 x2 xn where and independent. This is what we want to show. This is, if you remember, rewriting of the branching process for the number of progeny in terms of the random walk, it looks something similar to that. We wrote a new random walk where it started with 1, and every time I moved, I added an x1 and subtracted a 1 from it. And looked at the earliest time that this process hits 0. And that was the same distribution as my total progeny that we have seen so far. So just to recap, we had this process S0 prime was 1 and Si prime was 2. Si minus 1 prime plus a new copy of x and what we define was the T prime for this T. And T prime and T had the same distribution. Should really think about that's what this x1 plus x2 to x will be like. It's an interesting result. The total progeny distribution can actually be written down nothing but summation of all these IIT problems. So can you give an example where it is useful? Because this distribution is not very kind, except for some special cases. So can you give me a special case where the distribution of additional random variables of independent random variables is we can do something with it. Manju, feel free to jump in.
Yes.
So suppose this result is given to you. How do you think you can apply? This is a nasty piece, right? Adding even IIT random variables doesn't produce a nice random variable for which you can actually compute the right hand side. See, the utility of the result is if I can actually compute the right hand side. The left hand side is what I want to move. The right hand side is only in terms of the IIT copies of xs. So this is useful only if I can actually do something. So can you give me an example where you can actually control the right hand side? So what distribution do you know? where you add IID copies.
You get the same distribution.
No, I didn't say that.
Because
You get something which is tractable.
Poison.
Very good. So that's a great example. You add as many independent copies of Poison. All you have to getting is a new Poison, which is the addition of the beats. That's one example. Any other example that comes to mind? So that's why Poison branching processes are very special. Once we have this result, we'll be quickly able to write what is the total progeny distribution of a Poisson branching process. It's just one line. Any other examples comes to mind where you can actually add things?
Gaussian.
Gaussians. Okay, if you add Gaussian, what happens to Gaussians? Right.
They will give rise to another Gaussian random.
Are you sure?
Somehow.
So somehow to independent Gaussian. No?
Yes, I
Be careful. If that was true, then you can just keep adding Gaussians and keep getting Gaussian. I want to prove a result of this fact. The T, remember, is the total progeny size, a usual branching process. I want to write this in terms of just the random variable x, which are IIT copies. The result we want to prove is that the probability that the total progeny size is equal to n is nothing but 1 by n times the probability that the sum of these random variables take value n minus 1. Yeah, that's a very important show. Okay. It's useful to recall our reformulation of the branching process as a random walk. We started with 1, added 1 copy, subtracted 1, and we find the crime is equal to the earliest time at which this process it's 0. So that's really the interpretation the additions really are showing. So now suppose I give you the result, where do you think you can actually apply? The left hand side is what I want to compute, right hand side I'm giving you a problem. But still large number of additions of these random variables.
yes.
So one example where it's useful to add this is Poisson. If the random variables are Poisson, you add as many independent Poisson random variables, it remains Poisson with the rate which is just the summation of. So you get a simple answer out that if the branching process had a Poisson distribution, you can exactly write down the total progeny distribution. If you have any other example where adding IIT copies of random variables, you can compute something like this. Probability that addition of n random variables is equal to n minus 1. You're saying Gaussian, you're confident.
Addition of independent Gaussian random variables will give rise to
Question.
Gaussian.
Any other example? The Bernoulli don't work. Bernoulli you can binomial. What about exponential? That also doesn't work. Max mins are okay, but if you add exponential random variables, you don't remain. And here anyway it's a discrete distribution. So you have to be very careful. What we are interested in here is discrete distributions. All of this is discrete. So really, an example which gives significance to the formula is Poisson distribution. As soon as I write this, in one line I can write down exact Poisson distribution. It will do it. Okay, so any ideas what is this? Can you interpret this? Why should you even expect something like this to happen? Why is there a division of 1 by n? What is this one? Yes. That's the result we want to do. Would any size being n is not equal to this sum equal to n minus 1, right? Should there be a factor of 1 by n? So the sum of x's is not t, is not t. That's not by definition. It's what we want to do. If you want to neglect this, not know how to look at it, so you don't move ahead. Is there any way to see why? Can you give an intuitive answer why this should be accepted? What is going on? Okay, let me make it more than that. I specialize. Okay, so let's try to. So why I? So this is going to be general result, not necessarily for the branching process, but from here we can get back to the branching process. So why is that's the only property I need here. Adding the satisfied. But the value they take is minus. Now starting point. This is more to define complete new process. Let's suppose the starting point is scale. And extend k plus y1 plus 2. So essentially it's the position of the random walk. And steps starting from at h0, the heating time of 0, the age and SN. So first of all, yeah. So this random walk is in only. Yes, follow that. Then is the probability. So K is indexed here to make sure that you remember where we are starting from. K. Let's see. And K over N. Here's the K. I would like this notation of N being reused, but because I'm speaking to the book, it follows. We should really have used another index here. Because otherwise it's overloaded notation, if you think about it. This is some other time index, this is some other time index. Both are being represented by. So what is x0? The earliest time where this process is zero. What are we asking? That what is the probability that the earliest time I must began? It's nothing but the fraction k over n times the probability that the change is zero. See, here is some, these two events are not equal. Here this change is going on, random walk is going on. It might keep hitting zero so many different times. Here is asking for the first time. So essentially you interpret this. Suppose I tell you that the random walk is sitting at zero at time. What is the probability that actually the first time it is doing so? That is the connection between these two. So this event is just that Sn is zero for some event.
Yes.
That it's not telling you the first time, the second time, the third time. The left hand side is asking you this is happening for the first time. So given this information, what is the likelihood that this is the first time? And that is connected by this k over n. So suppose I use this result, can you recover the previous result? What would be my yi to recover that result? What would be the k?
One.
Right? My starting position is 1. I start the process with 1 position. So what should be yi? So that I can port that result into this.
Xi minus 1.
That's the recursive way. Remember, the process starts at 1. And every time it's essentially adding 1, subtracting 1 and adding a new xi. So this is what you should treat as yi. That's what is happening in this. The minus 1 is absorbed inside the yi. So if you use this and make sure that the Markov property of the random walk, this once you do this, you'll be able to say that is done. Alright, so now how do we do this? Now this has nothing to do with whatever you are seeing so far. Everything is on the board to prove this result. So at least for some trivial cases, can you verify that this result is true? So what happens when n is 1?
Sn to be equals to 0, y1 should be equals to minus k.
Minus k. Why k?
So that Sn will be equals to 0.
But you can't take any value less than minus 1 anyway.
Yes.
So why not start with fixing k equal to 1 and n equal to 1? So in that case, is the right hand side equal to the left hand side? So what is the probability on any one of the sides when n is 1 and k is strictly greater than 1? What happens in these two cases? At least relationship should hold. Otherwise, it's meaningless formula. So what happens in k greater than 1? What is this probability difference? H0 is 1. When k is greater than 1.
Be 0.
So LHS is 0. What is above RHS? What is probability of Sn equal to 0? When n is 1 and k is greater than 1. See, y cannot take any value less than -1. So there is no way to cancel it out.
Okay.
That is why both these properties are defined. That's why this condition is important.
Wait. When k is greater than 1.
Yeah. How do I hit 0? Let S1 equal to 0.
Okay, for any one to 0.
What would k equal to 1? Now they're not anymore 0, it's something else.
Why it has to be -1.
No, what is the probability? The probability is exactly y equal to -1.
Yes.
And that k then cancel because both of them are 1. So both sides probability is equal to probability y. So at least we are good to start with. Because for induction, if I want to prove something like this, starting step was key. Now I want to go to n greater than. So induction on n greater. Proof is not very instructive. What we want to do is open it up. Conditioned on the value of the first random variable y1. Always remember, most of the tricks on all these results are essentially captured by taking the conditioning on the first number of variables. We have done this before also. You condition on the first, like the number of children you produce at level 1, and then everything else essentially restarts at high level view. That's why I should be able to do this again. Now, want to condition like this, where conditioning over y1 is equal to some. And that some number cannot be less than -1, so I'm going to start from s is equal to minus. Now, what can we do? We know certain properties of the number. What can I write this? Is there any other way to write this in terms of p k plus s? Is it these two quantities? Do they have any connection between them? Remember the subscript here is the starting one. Okay, so rather than starting at k, if I want to start at k plus s, and ask for probability of h0 equal to n minus 1 instead of h0 equal to one step. So h0 equal to n minus 1 is you're hitting 0 one step earlier. That's h0 equal to n meant that it took you n steps to reach 0. N minus 1 means just took one less step compared to. So is there a connection between these two probabilities? Remember, yi is an IID.
They are equal.
They're equal.
Yes.
Because I'm just shifting my starting point
Yes.
and taking one step less.
Hmm.
And this is under conditioning. If it was just conditioning with a random variable y1 itself, that would be true. I've conditioned with y1 equal to s. So I've already specified how much value y1 takes. That is same as I just shifting my starting point and taking one step less. So this will actually be equal. Now I claim that you can use the induction hypothesis. So what is the induction hypothesis tell me? And for which you will be slightly careful, but I discuss them first. The result we want to grow, I can use that because of the induction hypothesis. I've gone one step back. So what would be that answer? We simply k plus s divided by n minus 1 times.
What is induction hypothesis?
So induction I'm taking, I'm going to prove this. Taking induction on n. But n equal to 1, I've showed you that this is.
Yes.
Now I can use this for any n, assuming that the result is true for n minus. So now, by doing this, I will simply come back to a new starting point and an n minus. This should give me what? Should give me that is equal to minus k plus n divided by n minus 1.
Right hand. What was there in the right hand side?
So S n minus 1 because it was Sn equal to 0. And how much what should I put here? That's why I'm giving this index. Where my starting point is. So if you look back at it, my starting point was k. I was looking at n steps reaching 0. Now starting point is k plus n and reaching 0 and minus 1 steps. Let k becomes k plus n becomes n minus. That's what I have. And then, but do I need some care? Go from here to there. You have to at least notice it. But to make sure that k plus s is greater than or equal to 0 at least. Because probabilities being negative doesn't make any sense.
Yes.
So why is that true? Is the question clear?
Yes.
There is some care needed to write this formula. Because if k plus s turns out to be negative, this is a meaningless answer. So why is it true that k plus s is in fact greater than or equal to 0? What is the value of s can take?
Minus 1 to
And what is the value k can take? By default, greater than or equal to 1. You know, allowing starting points to be zeros.
Okay.
That is why k plus s is in fact always greater than or equal. So k equal to 0 is meaningless for all this. Because we're starting with, if you start with 0 particles, you're not going to grow anywhere. So starting point is always 1 or ahead of 1. You can actually do this for even more than 1.
In random walk, I can.
You can do that, but in this process, when we are starting things, k is at least greater than or equal to 0. Otherwise, none of this makes sense. Because we are assuming certain conditions on y's. So this is true, but at least you notice that what I'm doing is not incorrect. Okay, so now from here on, what do you think I should do? I want to somehow go from this p of k plus s, Sn minus 1 equal to 0 to p of k Sn equal to 0. That's what my. So I've got what I really want is this formula. What I'm missing, there is a n minus 1 in the denominator, that is missing. And there is a k plus s extra city which I want to get rid of. and inside there is a k plus s and there is Sn. Well, I want Sn minus 1. What I want is to recover first delta. So what do you think I can do? This will be very little you can play with. All you see, this is kind of frozen. There's nothing much to do here. Now, what is this you can play with? Think of the conditional expectation of y1 given Sn is 0. So that's the only quantity I can really compute now. Everything else I have computed. So there is some randomness left with respect to y1 here, which I can try to capture somehow. What I'm asking is, what is the conditional expectation of y1? Let's go to this next one. An interesting point here. Conditional expectation. Starting point k y1 given Sn. And first thing to notice is it equal to expected value of y2 given Sn equal to 0? That might simplify matters a lot. Or y3 or y4, whatever. The question here I'm asking that is this quantity equal to the expected value of y2 given Sn equal to 0 also? The information given to you that Sn is 0. That's all the information given to you. What kind of information can you extract about y1 and y2? Is it any different?
yi is our IID.
Y is the IID, but that doesn't mean that once you condition there is an IID. So you have to argue. Always remember, IID random variables can become suddenly correlated once you condition. But now the question is, given that the information I'm giving you is Sn equal to 0, are conditionally y is independent or not? No, right?
Sn is k plus sum of y's, right? Symmetric between all y.
Yes. So whatever information you get about y1, the same information you get about y2. There is no distinction between. So what is Sn? Sn was
k plus
A plus all I'm telling you is Sn equal to 0. Then I'm asking what is 2? Very high. So suppose if it was, can you compute this one? Suppose this is true for now. Can you actually compute this? Actually, if this is equal, you can actually compute this one. That's enough. And why is that? Because of linearity of expectation. Then expected value of 1% equal to 0 is nothing but 1 over n summation expected value of 1 r. Yes. Right? If that is true, this is also true. Now what can I do next? Again, push the expectation inside the summation inside. That's the power of linearity of expectation. This is also equal to 1 over n. Expected value. Summation. Now, what is this quantity? Given as an equal to 0. The summation of is
minus k.
it's exactly minus k. There's nothing before randomness left in this. So then this is nothing. So if I have this, I can actually compute this. So now convince yourself, I mean, that's true. At least I handle it. This is symmetry, I would accept that. See, if I replace this location of y1 and yn, it wouldn't matter.
No,
That's good enough.
no, but this
All I'm conditioning is Sn equal to 0. If y1 come first or y2 came second, or y2 came first or y1 came second. Not matter. There I had it.
yes, but there should be some correlation between the variables for Sn to be 0, right?
That's okay. All I'm asking is the expected value of this. I'm not saying condition on Sn equal to 0, y1 is independent of y2. I'm not saying. That's too much to ask for. All I'm saying is the relative locations don't really matter. If you look at the first index here, that's what for y variable, first index, and the second index. If I were to put this in a black box and just compute it, you cannot be able to tell the distinction. So all I'm telling you is the summation is the because y1 comes first or y2 comes later or y2 comes faster. The condition expectation for this. Now suddenly we are back in this. So now tell me how do I go from here to some quantity which resembles the conditional expectation of y1 given Sn equal to 0. I have lots of things here. You can see through it, it will be very nice. So what I want to do, some way writing this in terms of y1 given Sn. Now I have an exact answer for that, which is in the correct form, a minus k over n. So what you do, simplify this into some form of this times the next step of it. And remember how we went from here to here. I can always go back. So I took this using the Markov property with k. What did I do? From k to k plus s and n to n minus. Now I have n minus 1 and k plus s. I can go backwards. I can of course write this as beyond k. That is that is tell me one comes line, how do I somehow involve this quantity? The k over s minus 1 is useless. There is no more randomness left in the k over. So if I put that out, it will be k over n minus 1 summation. Yes. Okay. Should object. See, from here to here, it was a condition. So if I go back, it could touch the condition. T1. This is now is equal to 0. T1. Plus times plus this is the interesting one s over s times what is the first term? That is straightforward. Not total probability. Isn't it not just probability of KSL equal to 0? Condition and add. Multiply by probability. This is nothing but K by n minus 2 times probability that SN. What is the delta? Now we will invoke this. This is the next setting. You really think about it as some expectation being taken. Now we just flip around the joint distribution in the reverse direction. What we've done here so far is condition on y1 is equal to s. You can do the reverse.
Condition on y1.
S is equal to z. Can be written in two different ways. Now I can start writing it as probability of s equal to 0 times the probability of y1 equal to s given s. And s when is getting multiplied from the outside is exactly this.
How are we getting that expectation thing?
Yeah, what is conditional expectation of y given x? What kind of random variable is that?
Y1 into probability means y1 equals to x given Sn equals to 0, so Sn over
Here's all things.
okay.
So this is nothing but 1 over n minus 1. 1 over n minus 3. S equal to 0. This we like. This answer I already have.
I don't understand this terms.
S over n minus 1 sub over s.
Condition y1 equal to s. Y1 equal to s.
I can always flip it around. Is it the same? That's all. I'm just pulling this out, rewriting this is nothing but the conditions.
Okay.
Now, given that I already know what the number is, I can plug and get back balance. So hardly any space left, but this is common. Probability of Sn equal to 0 is common. Here it's k over n minus 1. Here it is minus k over n times n times. This is easily cancel and you'll get what you have. Now there is nothing more than this. This term and this term is common. This is minus k over n. So you get k over n minus 1 minus k over n times n. So exactly the formula we want. This. So the proof really is not very different, but the implication is good. Now what it tells you is, like, especially for Poisson random variable. Very good property of equal to n. Tell me just 1 by n. And x1. So for Poisson random variable, you get parameter lambda. Now this property. So
e to the power minus n lambda to the power n minus 1 by n minus
So this will be this much.
2. E to the power minus n lambda to the power n minus 1 by n minus 1 factorial.
Okay, now this is 1 by n. So what will you get suddenly?
1 by n
So I get n factorial
is
e to minus n lambda. And
n
this is another person.
yes,
Why? But the
1 by lambda times, that's 1 by lambda times.
Is this a known distribution?
Sorry,
Is this a known distribution? Is it not polar? So what is missing in that person?
n lambda.
Yeah.
If we multiply it with n lambda, then
Why is that correct? You think there will be a new Poisson distribution
yes,
with n lambda.
as me.
So it's just close to it, but not actually there. So an approximation, if you really wanted to make, you would make that. But at least you can precisely write down the distribution. That's not very good. Then if your branching process was not distributed, the number of protein you should see is exact as now. There is no approximation. It would have been nice if it also turned out with a higher distribution. But something like this will happen for Poisson in terms of its conjugates. Remember the conjugate, right? What was the conjugate? Condition on the extinction, what is my new distribution? Okay. Px for my original distribution. That defines Px prime to be beta to the power k minus k. So this was the distribution you see if you condition your branching process on extinction. So it's called the conjugate. So now, if my branching process for Poisson, what is my conjugate distribution? The question clear.
Yes.
So we wanted, but we didn't get everything. Here, we didn't get back a Poisson. It resembles it, but it's not really Poisson. Now, in this case, what can you say about the conjugate? The x was Poisson. Is x prime also Poisson? You don't have like difficult computation. You remember what is the property of eta? Eta satisfies only. So eta is equal to Jx of eta. What is Jx for Poisson distribution with parameter lambda? This is the definition. Dx of s is to the power x. For x we call on lambda. What is g of s? Did this. What is g of x? This is right in the open it up, intersect me.
So it's a exponential
X to the power e,
lambda times x minus 1.
lambda to the power t. T factorial given. T to the minus lambda. Right. So what are the meetings on the
T from 0 to
this is a nice form.
Exponential lambda times x minus 1.
Minus lambda.
No, exponential lambda times s minus 1.
Different.
X of
That is in fact correct. Now if I put it back in my eta equal to gx eta equation, what do I get? That is the box. And plus because t to the power. Just exponential something very hard. So now what is the value of eta?
eta equals to e to the power lambda times eta minus
E to the power lambda times.
eta minus
Okay. So let's suppose this is my relation number one. You can't simplify this anymore. But this helps you in actually doing this. So what I want to find is what is my conjugate problem. I know P of x. This I know. Now I know a relation to beta satisfied. And then I know Px prime. That's something interesting. Answer. So put it up, pretty simple. Just write eta to the power k minus 1 into the given Poisson distribution. So pretty interesting in happening. You have to use the relationship one. Do it. The relationship I have. It minus lambda is how much?
Okay. Eta by e to the power
So I wanted to replace this. Let's say it works.
eta times e to the power minus eta lambda.
Okay, so let's keep it here. Lambda, okay. And eta, so
E to the power and e to the power eta lambda.
just my. Back again. So how much do I get? Yeah, eta to the power k. Lambda to the power k. E to the power eta lambda. It- All this is to do with this issue. Suddenly, it is. Suddenly, conditioned on the extension, the new distribution also is positive. With the new intensity, it is eta times lambda. And eta lambda is less than one. That's what is there to say.
Why gx will be the characteristic function of the Poisson distribution?
Why? This is the definition. And for any distribution, eta satisfies this.
Eta satisfies this,
Yeah.
then why it is equal to exponential lambda minus one?
You just told me.
No, I mean, why it is, we said Px is according to Poisson random variable. And then eta,
I don't understand.
so Px is distributed according to Poisson random variable.
The extension probability for mapping process with distribution together. Satisfies eta equal to g of x. We are solving for this function, which you told me this is the correct formula. Just plugging back the eta and again this relationship. Pretty clear. All I know is I redefined it and proven that the new distribution, condition on execution is nothing but this renormalized distribution, which is called a conjugate. We are looking for what is this new conjugate distribution looking at. So when the original distribution is followed, in terms of the conjugate distribution also is followed, just with the reduced intensity. That's all. So for most of the interesting properties are restricted to or limited to follow. You don't get all these nice answers. That distribution will not work. You get very ugly answer. So this is the nicest answer we got. The previous slide was closest to nicest thing. This would have been very happy. You would have been very happy because this will also work. But it's not. But at least you can characterize it exactly. Okay, for Poisson distribution. When I say Poisson distribution, essentially the branching process. With Poisson. Now. What great that P is equal to N. We have exactly computed it. I just want to look at the acid matrix. Is 1, 2, 3, 5. Q and now P minus lambda. Get this file. The bottom line is that this is 1 over n to the power. That's not. So this is also called power law. So again, is decreasing almost linear. You don't say this distributor to be called power law distribution. Whose probability that makes it beta. These are called power law distribution. So the bottom line will be that for a branching process with further random variables, you actually have 1 over n 3 by 2 growth. This is our combined. This is the data from our application.
This thing, how did we get this?
Just
Okay,
take this formula and apply the asymptotics of the factorial. That's
okay.
there's nothing interesting about it. But it's good to know that this formula can be simplified to book like this.
One minute.
There are some other terms in terms of marks, the dominant term. See, everything else is independent of language. How scaling it then is actually 1 over. All you need to do is just apply Sterling's approximation to the vector. But it's good to know this, you might need it later. Like for a branching process with Poisson distribution, the rate of growth of protein falls down into the power of 3 by 2. So final thing in branching process we will do the following, and we will building up forever in the earlier part of the course. My update was connecting. But we want to say that in terms of the. So if I run a branching process with binomial distribution, in parallel I run a branching process with Poisson distribution with appropriate parameters. What I want to show is that the progeny distributions are particular. That's really what we want. But as soon as we go to discrete graphs, everything will be binomial. But we want to approximate everything to Poisson because Poisson is where I can do this. And that's why we did all the setup to make sure that these two distributions can actually be coupled. So that was an important exercise we did. Then you can find the coupling between binomial and Poisson distribution. So that the probability that they don't match is small enough. Then rewrite that. That's essentially what we're trying to do. That we have done in the earlier part of the course. That was essentially the reason to introduce all the coupling there. The result I want to show is the following. So let's call this. So I'm going to write n comma p for binomial and p lambda for the Poisson. So when I'm taking of branching process with Poisson distribution, we will represent everything of p lambda and for the binomial n comma 2 parameters. So p is the same. P n P where here in K. Is it clear what's going on? They're almost equal, except for this error term. Now the error term going down, one by n. So to remove the coupling result, what was the coupling? Remember, we were able to find the coupling between Poisson random variable and binomial random variable, where the probability of they don't match was exactly at most less than equal to lambda square by n. That is precisely the transfer. And write that number. That's all we should really think about.
What does t to the power lambda?
It's not T in power. This is representing in this process for that T. If you want to keep, I can work below. Would you tell the person?
No.
There's no power. T lambda is nothing but the total project is same, but the branching process has one distribution with parameter lambda. And I'm not writing here and again this distribution. So what is the implication? The implication is that the difference is very minimal. It then goes large. And if I can control this, you can understand. This one has to be slightly careful that as you're looking at larger and larger scale, this term also is more and more sometimes. But still, it is still going down as where it is the number of the NP parameter. And lambda will be essentially n times 2. That's when they match. So lambda. Okay, how do I prove something like this? So given, suppose I give you a primitive. Let me say x is get something with this x prime and y, which is coupling. So x prime and x have the same marginal distribution, y prime and y have the same marginal distribution. And what we're able to show x prime is not equal to y. How much smaller? This we have shown. There exists a coupling, like coupling was nothing but the maximum coupling. The definition of maximum coupling. Minimum coupling. That's what we showed. If you look back at it, thanks.
What is maximal coupling?
One particular coupling, and that's what we use to show this. There's so many other couplings possible. Couplings are not unique.
What is the coupling?
Yeah, coupling is that suppose you're given x and y and which are no connection to each other. I will create an x prime, which is the same distribution of x. For y prime, is the same distribution of y. And now I can have any arbitrary connection between x prime and y.
Okay.
So essentially, you're producing, you should really think of it as a joint distribution x prime y prime, which is faithful with respect to x, faithful with respect to y, and have arbitrary joint distribution. What I really want with this arbitrariness is what is the probability that they don't match, and I want to control that probability. So I want to connect. So coupling is nothing but coupling in the usual sense that now x prime and y prime have something to do with each other. So if I know something about x prime, I should be able to say something about y. In the original space, I have no connection. But in the new space where I'm defining a coupling, I should be able to establish something like this. It's in the nice way. So suppose I give you this primitive, then such an x prime and y prime like this. How do you go back and do something like this? So give me at least a and maybe argument. So suppose that the next slide was 0. Then what would you do? The upper bound was 0. That is x prime and y prime are always equal. Now what would happen? which term will disappear from the board now?
E and K.
Essentially, because the two distributions are identical.
Same.
Whatever value t takes on the left side, the same value t takes. Now I have some first factor. Then the probability with which I make a mistake. So suppose I was predicting one process from the other. The probability of making a mistake is at most lambda square. Now how do I do see this?
The left hand side is equals to 1 minus t probability t less than equals to k. That will be giving us that from because of that coupling thing. That thing will be having distribution same as x prime or like that. Same for the right hand side we can do.
So that is okay.
Hmm.
How will you proceed further? Because that is for individual random variables. T is not that individual random. T is a summation of lots of random variables.
Okay.
What I have coupling is between the progeny which gets risen by at each step, or each node gives rise to number of children which is distributed by binomial or causal. That I have. But I need to transport that to the T. T is a total number.
Okay.
But what can bound the difference of the first term and the second? Can you give me, not in terms of EN, we have the final answer. Can you give me in between quantity, which you can always upper bound at difference by? So probability, what I'm asking is probability of T greater than K in the binomial case minus the probability of T greater than K in the causal case. Is there a crude bound you can count? Not in terms of ENs, just the usual motions. Just in terms of T's and T lambdas. You can think of any two random variables, not even T's. What is the probability that x greater than K minus y greater than K bounded by? That will give you everything. Here. What I want is suppose T lambda. If you get to bound it, in terms of only T and T lambda.
Is Markov's equality here?
Markov is something else. These are probabilities difference in time bound. Markov will tell you something else. One, you can possibly bound this term and this term separate. One to bound the difference of it. So think about it. Is this true? Very important. It should be different.
Yeah.
So give me an implication. Why should you do? You're doing term by term. With first term, that's at most the first term, and then you can choose at most the second term. So it is at most the max of the Right, just one of these terms. So being greater than K. In terms of both P and T lambda, how do you write it? Equality. Equal to P greater than equal to K. P lambda is equal to K plus that is correct. Now we can write the same thing for P. P lambda. Just subtract this out. Subtract this, compare it down. That's all it is. It's a trivial relationship. So now, once we have this, what is our objective? We want to bound the symmetric. Think of it. If I bound one, the other one is the same way we bound. So all I have to do is to handle one of them. So now tell me how to handle one of them. What am I trying to do? If T is greater than K, but T lambda is less than K. That's the only event I need to connect. And what are these?
Progeny signs.
But there is another way to write it. P has the same distribution as S prime 0 equal to 1. So you know that this is K. Is the same distribution as this. Now, let's suppose I only want to control one of this. The second one is symmetric. I don't know. When T is greater than K, but T lambda is less than K. What has to happen for this symmetric? So T is greater than K, but T lambda is less than K. Can you point out at least one event that has to happen for this to be true? That's pretty much it. The crux of this is just to identify one particular event that has to happen. What does T greater than equal to K mean? Then the process is not hit zero. While the process with the T lambda is going to hit zero before K.
Sorry.
What is the meaning of T greater than K mean? That when I'm running the branching process with binomial distribution,
The okay, this
that this hitting event happens at or after K.
uh,
While with T lambda, it's happening strictly before K. So for that to happen, what has to happen? There's at least one random variable which should not match until 10 times. See what is driven by this is xn. Let's see one process that called an xn, another process called an xn plan. So if these two don't match, there at least has to have one random variable which doesn't match.
Yes.
But by what time? By a certain time, this is the time index dimension, x1, x2, so we have seen here. x1, x2, x1 down, x2 down. This gives rise to P. This gives rise to P. What I do is T is greater than K, while T is less than K. What can you say about x? By what time? At least one of them don't match. So
Roughly minus.
Before K.
Okay. Strictly.
Strictly before K.
Okay. So let's call that index something. Let's call it whatever you want.
J.
G.
J.
J. Okay. J. Now what can you say? Suppose there is a none. So whatever you extracted, if this is true, then there is at least one random variable at which place they would match. And from my primitive, I know that that happens with the probability which is small enough. That is all I'm going to play with. So, to be complete, but I need to catch the idea. What have we done? We've essentially taken the difference between the two, and this is the trivial law. Nothing much is done. Now pick any of the two, any of the first event. Telling you that T is greater than K, that is, I have not ended up before K. While here it's saying by K, it's a. So for that to happen, by time K minus 1, at least one of these pair of random variables cannot match. But if they match, then this would not happen.
Yes.
And what I know is that because of my coupling, that probability is small. So this probability better is small. That's all I'm going to play with. The idea should be clear. Circus is you just put the round everything. Now we just start writing. S before K. Like that. Excel. What you just said again. Instead of calling J, I'm just calling it S. The follow the S. Oh. Now I will write now S can happen anywhere between 1 to K minus 1. To add all those possibilities. And also looking at, let's take the earliest suggest. There will be more than one. I'm just looking at the first one. Starting from the so that automatically means for all the previous one, they are matching.
Yes.
And this implies this. That's pretty much obvious. Okay, now what can I do to simplify further? Directly, this looks imposing, right? But some independent has to be extended. Now, what is independent of what? So, what do events T and T lambda depend on? So if I say t greater than equal to k, how many random variables that event depends?
At least k plus 1, x1 to
Why
x.
k plus one? Why not k?
Because t is strictly greater than k, right?
So if I tell you the history,
Up to k,
k
then
minus one,
okay.
will you be able to identify it completely?
No.
When I'm saying t is greater than k, and if I tell you the history up to k minus one, you should be able to tell me. It's a complement level, right? T is greater than equal to k. So if I want to tell you everything about until k minus one, you should be able to tell me
Yes.
whether t is greater than equal to k or not equal to k. So it only depends on the random variable c until k minus one.
Hmm.
So now can you use that somehow? That's the final constraint of this. There is something more sitting here, you're not noticing. So this was the earliest such case. So these random variables are exactly equal. If you put this condition and this condition, what can you say about t star? Or sorry, t lambda? So just put this condition and this condition. The t is greater than k, and until time s minus 1, the two random variables are identical. So what can you say about t lambda? This is clear that these two random variables are exactly identical. So until this level, which is s minus 2, they're exactly identical.
Yes.
But my t happens to be greater than 2. So what can you say about t lambda?
T lambda should lie between s to k minus 1.
I don't care about k minus. All I care about is it greater than s minus 1?
Yes.
So is it s or s minus?
S.
Why?
Up to s minus 1
It
there.
doesn't happen. So it can only happen beyond s or at s or
At
beyond. So that's something which you are missing. So now this and this can be combined. Right, this is a probability that lambda is greater than s. Now apply your fact that you can discuss. Are these two events independent? The fact that t lambda is greater than s, greater than equal to s. And at s, these two random variables don't match. What does this depend on? It only depends on all the previous random variables. To decide on this, all you need the information is only into s minus 1. And the random variables produced at time s are independent of everything that has happened so far. So these two bits are actually independent. So I can write this one. Now, if you look back at the answer we wanted, to spare it is for a moment. I have the coupling probabilities, which is the mismatch of the coupling, times something. Added to s going from 1 to k minus. And what was the answer I was looking for? Okay, the answer I was looking for. So the coupling is already sitting here, and nothing but exactly what I was looking for. The probability that t lambda is greater than s sum from s equal to. So one of the terms I am able to form. But the second term is symmetric. I don't have to work hard. So this term is nothing but symmetrical term. So you exactly get what you want. So this is essentially this probability is almost. This is better. So this is eventually the answer is. Now you know why we did all the coupling. So eventually you're able to use the coupling to show that the two branching processes, one run with a binomial distribution, one run with a Poisson distribution. Actually, a very close, and then goes. And this result is repeated using. All right, questions.